I want to start off by saying we're about to watch me read a book, which isn't going to be very interesting. I know my voice is annoying, but trust me, if you can make it through to the end of this, you will come out of it with some knowledge, quite a lot of it. If you can listen to what's actually in here and understand what it means, you'll know more about saw chain than probably 95% of people. So, as we can see, it is branded. Everything in here is going to be Mcculloch, but doesn't make the information any less valuable. We need to start with the very basics. So obviously identifying the parts of the chain. As long as we all know this, we have those common terms. So we have a left-hand cutter and a right-hand cutter because saw chain needs to work in pairs. We need the same thing to be happening on each side. It all needs to be equal. Through the center of the chain, we have the drive links. They call it a center link or a drive link. They have the lower tang section that actually makes contact with the rim or the spur sprocket and provides the drive to the chain. Either side of them we have tie straps, side links or tie straps. Chain in a normal sequence will have our left hand cutter. It'll be sandwiched on one side of the center link and a tie strap on the other. The next drive link will just have a tie strap on both sides. That's our blank strap, and then we'll get our opposite, our right hand cutter without straps. That's the basics of saw chain. Obviously skip sequence or alternative sequence chains will have different amounts of blank straps in between the cutters. Very basic so far. Next, we're identifying parts of our cutter. So obviously the top plate is that upper section, the side plate is the side section of the actual cutting tooth. The bottom of the cutter, this applies to the tie straps as well, has a heel and a toe. Heel at the back, just like your foot, toe at the front. That is a section that rides on top of the guide bar. More modern chains are slightly different in the shaping. There's been changes made to make them more efficient, basically by having less friction of less parts on there, and also to have the heel of the cutter raised to absorb vibration and impact when the cutter first contacts wood. We have the notch on the bottom. This is for engaging with spur sprockets or with the nose sprocket on a sprocket nose bar. We obviously have our rivet holes, so we can attach it through, our depth gauge at the front, and we have a section here labelled a gullet. The next thing we're demonstrating is different types of depth gauges. This is viewing them from the front. The regular depth gauge is just straight up and down. We have two different versions here of offset depth gauges. This one comes up, makes one bend out with the cutter. The next one along comes up, bends out, and then straightens up again. We get a description of some of the things going on here. So our description down here, I'll put the text up on the screen for you guys. Saw chain has two types of cutters, a left and a right hand. I don't like the wording there, but we do have a left and a right hand cutter, so that's fine. The cutters are shaped so that the inner top edges of each left and right hand cutter overlap. The cutters do not cut wood in slices but remove it in small chips or bites. Wording there is not great. The important thing there is that the cutters overlap in the center. So the top plates over here overlap in the center. If they don't overlap, it leads to some problems, which is described later on. Each cutter has a top plate and a side plate which are shaped to a fine edge and which regularly need resharpening to keep the chain at top performance. That's obviously what we do every time we grab a file. The outside surface of each top plate and side plate is given a hard chrome finish to keep the edges sharper longer. You've all seen it when you look at your cutters, that's what's happening. That's the basics of the cutter. Back to these depth gauges. Some cutters have offset depth gauges. Offset depth gauges promote smoother cutting by helping to control the side plate width of cut and thereby lessen cutter chatter and chain wobble. Cutter chatter occurs when the top plate tries to grab too big a bite and breaks the chips out rather than cutting it free. Wobble occurs when the side plates pull too far into the wood and make the chain lean from side to side. Chatter and wobble are conditions damaging to chain. So we've got our cutters, a left and a right. Due to the angles that we've filed on them, they are going to try and drive out into the walls of the kerf, which we'll explain better later. The more angle, the more they want to do that. The idea of the offset depth gauge is to lean out towards the corner, and that prevents them from trying to pull over as far. This is commonly done on most modern chains. Next we move on to cutter chip clearance. We're going to talk a fair bit about chip clearance. We'll just leave the picture there for a second. Let's look at the text description. Chip clearance is the action of removing the chip after it has been cut. There are two types of chip clearance. These are number 1, cutter chip clearance, and number 2, chain chip clearance. So cutter chip clearance is the ability of the cutter to release the chip after it has been severed from the wood. That is what we're dealing with here. You can see they're using a term called coined. You will see this used again soon. When they're referring to coining it, they're basically sandwiching it or squishing it to create a thinner edge. These are both a chipper style cutter. We can tell by the big rounded corners, but you can see what's occurred. They have thinned the top plate on this one. By doing so, it's created more room down in this bend. By creating more room there, it allows us to deal with part 1 of the chip clearance issues, which is cutter chip clearance. When we look at a cutter, that's a blowing up one, you'll be able to see that there is a channel that's formed under the top plate. This is called the chip channel. After the chip has been formed, the chip to escape the cutter needs to travel through this section and come out of the rear of the cutter. The majority of modern chains are coined or thinned up here. The amount of clearance changes with the cutter style, which we'll get into later. As it mentions here for part 2 of our chain chip clearance, chain chip clearance is the ability of the chain to clear the released severed chips out of the kerf without recutting them. So what we want to happen is for our chip to roll out the back, get to that blank strap and not interfere with any other cutters. If it has been recut on the way through, we are losing efficiency. It gets recut because it is jammed the following cutters. There is more to chip clearance, a whole lot more, but these two basic principles is really what needs to be understood about it. Next we move on to kerf. So this describes kerf and essentially the two types of it. We'll just quickly read it and then we'll explain what's going on. There are two types of kerf, wood kerf and mechanical kerf. Wood kerf is the width of the cut that is made in the wood by the cutters. This would be our wood kerf down here. Cutters have a tendency to pull outward away from each other so that the wood kerf is always a little wider than the mechanical kerf, which is necessary for free movement of the bar and chain during the cut. So as I was saying, because we have a left and a right hand cutter pair, due to the angles they're sharpened on, they tend to want to deviate out slightly. Because of that force, as they get pulled out, our wood kerf, the gap that's actually cut in the wood, will always be wider than our mechanical kerf or the beginning kerf, the width between the two outer working corners. Mechanical kerf is a distance from the outside edge of the side plate of a left and a right hand cutter. That's basically it. If you've ever heard of terms like narrow kerf, it's where they've tried to narrow that distance up. We can get a lot more detail on them later. Here we describe some of the basics related to our center links. So a regular link is the same thickness from the top to the bottom. A coined one is thicker at the top and then becomes narrower once we drop below the section where the tie straps are into the actual drive link. That's obviously the shape of our drive link or center link. Our two rivet holes, our tang, the lower section is referred to as tang. You can see we have a hook here that has a purpose, which we'll get into later. The center links are the drive links of the chain. The tang is a part of the center link pushed against by the sprocket to move the chain along. The tang also rides in the bar groove and keeps the chain on the bar. So it helps that stability. Remember, the cutters are trying to pull outside to side. So that means the drive tang gets that movement going in it. Each job is to sit down in that rail and try and stabilize it. Chain gauge. So here we have our center link or our drive link. Remember from the image before. The measurements given here apply to current Oregon chains and Carlton chains. Still chains are different. The Husky chains, their own ones, their X-cut ones, comply mostly with that in 3/8 and 325. Still chains in 3/8 and 325, excluding the Pro series, your RS and your RM Pro, comply with this. Comply with this to a degree, but we'll get into it. The description here. In most cases, the gauge of the chain to be used depends on the diameter of the wood being cut. Trimming and cutting small branches and small trees can be done with narrow gauge chains on low power saws with short, thin bars. As the diameter of the wood increases, longer bars are necessary. Longer bars must be thicker to support the longer bar length. Thicker bars require a wider wood kerf to prevent the chain and bar from binding or pinching in the cut. A wider kerf means a wider mechanical kerf and as a result bigger chains, which must be made from bigger parts, including a thicker tang to support the drive and drive the chain. And the tang thickness determines the gauge. So, there is a lot to take in here. Like I said, this is current Oregon chains follow this sequence. Current steel chains are slightly different. As you can see up here, the upper section of the center link is 58 gauge. The lower section has been coined or thinned to 50, only below that line A. The 58 gauge in this case is the same thickness the whole way up. So is the 63. In Oregon, it is still done that way. The 50 gauge chains have a 58 upper, the 58s are 58 the whole way through, and so with the same with the 63. If you buy a steel chain in a 325 or 3/8, the low pro is different. Things change there. And in 325, the RS and RM Pro are different to this. But in general, for your 3/8 steels, everything is 63 gauge. To get 58, they coin it or thin it. The same with 50. If you run a 50, a 58 or a 63 gauge steel 3/8 chain, they are all going to be 63 in the upper section and it's only the lower that gets thinned. We can see our description there. Obviously 0.112, this is back from the days of big chain. Some harvester chain is still quite large, but for the most part, guys using chainsaws, we're not using anything that big. As you can see in the description, obviously as you need bigger, thicker, heavier weight chains, we require bigger, thicker everything. The advantage of running a 50 gauge lower is you can make the bars thinner, The disadvantage of that is the ability to support the chain. If you make the bar thinner, there's less overall rail on the top for it to sit on. I'm not here to tell you what's the right size for you. Do what works. Or more importantly, use whatever is commonly available where you are. Look for your bars, whatever the most commonly available bar and chain type is for your saw, that's what you use. It'll be the cheapest. Here we have some basic information on bar and chain and the relationship of the bar and chain gauge. So obviously our cutter sits in there, the lower section of the tang sits down in the groove. We've got our chain gauge and our bar gauge. You want them to match. So our bar gauge helps support the chain. This is one that's been either the wrong size or just been flogged out over time. It happens. It allows the cutter to lean too much. I'm not sure if this manual actually describes the correct way of checking that. Hopefully it does later on. The most underrated part of any chain is our side links or our tie straps. They're very basic. 2 rivet holes. These have a dimple, heel at the rear, toe at the front, notch in the center. Quick description. The side link is the connecting link between the cutters and the center links, as well as spacing the links between the cutters. Like the cutters, side links have a toe, a heel and a notch. The toe, heel and notch slide on the bar rail and help support the chain. The notch permits nesting of the center link of the tang when used with spur sprockets. Some chains make use of a special side link called a guard link. This would be a safety one. This special chain helps prevent small limbs or brush from being hit by the depth gauge and is especially effective in reducing chain grabbing and kickback. Grabbing occurs when the depth gauge is caught by the wood and jams against other pieces of wood. Kickback occurs when the grabbing action suddenly kicks loose. Here we have a small section on rivets. Obviously we've got our shank, our shoulder, our thicker section in the middle. So our shoulders sit either side there. That's how it sits in our center link. The rivets hold the chain together and act as bearings around which the center links can turn. Rivets are manufactured of a thicker diameter center section called the shoulder or the flange and the 2 smaller diameter ends. The shoulder is wider than the thickness of the center link to prevent the cutters and side links from being clamped together in the center links when the rivets are headed, thereby allowing the chain to be flexible. The 2 smaller diameter ends of the rivet are called hubs or shanks. They are long enough to provide sufficient material for forming strong and effective rivet heads. Now we move into cutter types. Again, this is branded. This is a chain manufacturer. So the names that are going to be used here obviously relate to that manufacturer. The cutter types, however, can be pretty universal. Promac cutters. These are a chipper. Mcculloch Promac chain has a round type cutter. We would refer to this as chipper. It is the easiest cutter to sharpen. It cuts wood fast and efficiently. Because of the round type cutter, each wood fibre must be severed several times before the fibre is severed from the kerf. These are recommended back then because they're easier to sharpen. You can only get this in 404 now. It's pretty limited, only certain places in the world. So the important thing to look at here is how this style of cutter actually cuts. Because of this large rounded section here, that is our working corner, it is spread over a very big distance. Bits of this can be damaged and it can spread that load out over a very large area. This is why this style of chain has the ability to hold an edge for so long. However, it cuts slow because round cutters cut each grain several times. Here's our top plate as it's working through. Before we clear the full width of the kerf over to here, you can see it takes multiple passes to sever those wood fibres. We need to wait for that to reach down here before they're all cut. It is not very efficient, is why progress was made over time to try and improve it, which leads us to the Speed Mac. Obviously, This is described as a semi-square cutter. Different manufacturers use different terms. However, the most common term for this style of chain today, it would be called a semi-chisel. I've done a video describing semi-chisels and the differences between the many different types. If you're interested to know more about them, I'll leave a link. But the description that's given here, semi-square cutters cut each grain fewer times. The working corner has been reduced. It is now much smaller. It still has to make multiple passes to actually sever the full width of the kerf. However, it is much less than what we had before. The other things that occurred here is they've changed the overall shape of the cutter. This increases its efficiency because we have less friction against the sidewall of the kerf. We've cleared it out. We have a bigger area through here to allow chips to flow, aiding with that chip clearance. Have semi-square type cutters with offset depth gauges for smoother cutting. Semi-square type cutters cut wood faster and smoother than round type cutters because they cut each wood fibre fewer times before the fibre is severed. The semi-square shape provides wider cutter chip clearance, and the cutters get rid of chips faster than Pro Mac chains, our chipper. The Speed Mac cutters can be sharpened with a round file. They rank second in smoothness, speed of cutting, and chain life. They are recommended for frozen wood cutting. The Speed Mac chain selection table gives recommendations of use. Next up, our Super Pro. Now this is just a full chisel chain. We can see here it can cut, it'll sever the fibres with one pass. This is why it's efficient. The reason it blunts faster and it will not hold an edge as long is because now our working corner is just that very little 90-degree bent. Super Pro cutters cut each wood fibre once. They rate excellent in self-feeding. This style of chain, a full chisel chain, will self-feed more efficiently than any other type of chain. If you time cuts of a full chisel versus a semi-chisel and just rely on them self-feeding, the difference in cut speed is much greater than it would be if you added some feed pressure. There is multiple reasons why different chains can self-feed differently. I will explain this later in a different video. There are two types of Super Pro cutters. Super Pro round file is a round file chain, and Super Pro square. Both Super Pro round and Super Pro square cutters require more care in sharpening. Super Pro chains are rate highest in cut speed and smoothness. Both round and square file chains are excellent in all types of wood under all types of conditions. That's up to you. People don't like to admit this these days, but sharpening a full chisel chain actually requires a lot more care and attention than a semi-chisel. It's all about that little corner. Our next section deals with chain maintenance. Alright, we're going to cover this just briefly just to show a bit of history of stuff. Obviously they had their three different types of cutter, their chipper or round, their semi-chisel, that semi-square, or our full chisel. It was available in S or R, so square or round. Pitch, you think it's confusing these days, just be happy you weren't doing it back then. You could buy 250, 354, 375, which is 3.8 essentially, 404, 500, 562, 750. It's not so bad now when we go, do we want a 3.8 low pro or quarter inch, 325, 3.8 or a 404? We're doing all right. They're the gauges they were commonly selling, a 50, 58, 63 and 122. And it was available in different assemblies. So our SS was our semi-skip, S was skip, and nothing listed there was our standard. Cutter filing angles, these are the same whether it was back then or now. However, we generally see different recommendations of side plate angles, but the way you measure them is still exactly the same. When it all comes down to it, this whole filing thing, the whole sharpening, it comes down to 3 angles and a depth gauge setting. Well, I can make it as complex or as easy as you like. At the end of the day, it all comes down to what you do with these three angles and how you set a depth gauge. Our top plate filing angle, they describe it as. I typically describe it as a filing angle. That's looking at our cutter from above and the angle that we hold our file on. Our top plate cutting angle, this is viewed from the inside. We can see this angle here. That is what we are measuring. We view our cutter from the inside, that angle. That's what we're concerned with. Then we have our side plate angle, which is our cutter viewed from the outside, and we measure our side plate angle. Our speed Mac angles. That's how they'd sharpen a speed Mac chain back in the day. 35, 60, 85. Pretty standard issue, right? Our Pro Mac cutters. 35, 60, 90. Some of them 85. Depends on which ones you had. Our Super Pros. These are our full chisels. Our round filed full chisel was done 30, 60, 80. These days, if you saw this, it'd probably be 30, 60, 60. Back then, everything used a greater side plate angle. Our Super Pro squares, 20, between 45 and 55 on the top plate angle, and 90-degree side plate. Currently available Oregon squares tend to run like that. I'm not really going to describe much of this. This is the Auto Sharp. The Oregon Power Sharp system is very similar. It is basically regarding the self-sharpening style chains. I'm just going to show the cards in case anyone has an interest. There is some information written on the back of each. These were the skills required to manually sharpen it. It required manually sharpening it to be manually sharpened every so often. Next, we're going to look at sprockets. So this is a spur sprocket. The pitch is the distance between them. We have our root, the face, and the tip. Pretty basic piece of equipment. Our spur sprocket. So how it works is the chain rides down in here and is supported on the notch on the lower section of those links. So the center link tang sits between the sprocket and the teeth. That is how they drive. Next we have our rim sprocket. The rim sprockets are different because the tang sits inside the rim and the chain rides on the outside of the rim. They have holes in them for the sawdust to discharge from. They need to face outwards when you put one on. This is a cloverleaf style one. Not really going to get too involved in that. What I will do is briefly touch on something. I will probably discuss this later when I deal with the entirety of chip clearance one day. Just going to briefly touch on this. A spur sprocket in general will be able to clear chips much more effectively than a rim. A lot of rims don't have the sawdust or the holes in the side to eject. Most of the smaller ones don't. These allow a better flow of the fines that get brought back to the rear. If you're having issues with your rails clogging, your bar rails clogging, a spur sprocket will generally do a better job of clearing them. I will go into that in detail one day when I do a bunch of chip clearance videos, or at least one big one. Bars. Here we are looking at what they described at the time as a standard bar. This was a hard nose. Remember, this is early information. So at the end of the bar, we have what they describe as a funnel. Because it's the only thing I've got, I'll just use this monster of a thing. That is our funnel at the end here. Bars are generally wider in the lead-in section. That is to help get that chain to stabilize as it enters the bar. If it's coming off a spur or a rim, we need it all to align. We need the chain to align. We leave it wider and it funnels in to help center that chain as it's running on. Obviously that transitions into the bar groove. They describe as the oil passage, our oil hole. Got our groove then, looking from the end, our nose rails. This is a hard nose bar, which oddly is what I just grabbed as well. Our adjustment holes, which is our bar retaining slot, and there are our oil holes from the side. Okay, so roller noses, these are not very common. These are different to commonly available sprocket noses. You can see the rail drops away before it enters that roller section. I'm going to put the description briefly up on the screen. I'm not going to cover it because it's extremely unlikely that people are running them. Here we have something much more common, the sprocket nose bar. This is what we can commonly get these days. So we've got our basic sprocket nose. I'll leave the description up on the screen for you. Information on bar length, cutting capacity of the bar, it sticks out the front. We'll mention some manufacturers describe this as a called length. So I have a Windsor speed tip bar that is described as a 36 with a 36-inch called length. So what that means is it's longer. It is about 5 lengths longer than the majority of 36-inch bars in that mount because there is a legitimate 36 inches out the front of the saw. Different manufacturers list them differently. So that's what's achievable with a single cut. That's obviously what's achievable with 2 cuts. So it's just describing what you can do with. All right, next up we have our sprocket chain bar combinations. So the information contained in this. Sprockets of the same pitch are available with different numbers of teeth. When changing to a different number of sprocket teeth, keep in mind that the power of the saw must always be adequate to drive the chain at the design cutting speed. Now this is where the information will be different compared to what we have now. Most high-speed direct drive saws are manufactured to drive the chain at sprocket speeds of 7,000 RPM or more when cutting wood. Typically common now is for it to sit somewhere between 9 and 10. Depends on the saw. Some of them get pulled down to like 7,500 or 8. Others generally like to be pulled down into that 9 region. It'll work out where the peak torque is on your saw. You'll find the happy spot eventually. A chain that is run slower than design speed will run rough, tend to kick back. It is easy for it to be stopped in the cut. In general, the following are true. Sprockets with fewer teeth can be used with standard chain on long bars in large diameter timber. Sprockets with more teeth can be used with skip tooth chain on long bars in large diameter timber. Sprockets with more teeth are also used on short bars in hardwood where high chain speeds can be used because of the finer wood fibre. When the saw power is insufficient, the use of a sprocket with a smaller number of teeth. This bit on the hardwood is interesting. I've had mixed results. Here it gives a description. They may have used a 6 tooth with a standard comp chain on a long bar. They may have moved to an 8 with a skip tooth on that same thing. They may have run a 7 with a standard complement on a shorter bar. Everyone is different. If you run rim sprockets, they are cheap. Experiment. Try it for yourself. Problem solving. Cutter filing problem. Too great a filing angle used. We don't really care so much how it happens. Hopefully you can figure that out. What we care about is what occurs when you do this. It results in a thin, sharp side plate which tries to pull the cutter sideways in the wood. This makes the chain wobble and cut a wider kerf in the wood. So again, we've got our pair. They naturally want to pull out. The more of that filing angle you put, the more it is wanting to pull out. The wobble causes the upper portion of the center link of the drive tangs to wear against the inner edge of the bar rails and results in damage to the center link drive tangs and to the bar groove. If the top plate angles are uneven as well as being too great, the wear will be even worse. If the top plate angle on a skip tooth chain is too great, the cutters can pull far enough towards each side to leave an uncut ridge of wood in the center of the kerf. I've experienced that one. I was experimenting with more angle with a skip chain. The cutters pull so far out it doesn't clear the wood in the center of the kerf. It does not work. Too small, too shallow an angle when you're filing. Say instead of your 30 you got 10. Now we all know this can work. If you're ripping wood, very common. Chain and milling guys know all about this. It results in a blunt edge on the side plate, obviously. Blunt edge on the side plate, and the chain won't feed into wood and will require more pressure to make it cut. That is another thing that affects a chain's ability to self-feed, that filing angle. The less angle you have there, the less it will try and self-feed, and the more angle you have, the more it'll self-feed. Cutter filing problem. Hook. A hook cutter is caused by using too small a file, holding the file too low, or pressing down during the filing stroke. It results in a chain that feeds and cuts very fast for a short period of time and then becomes blunt and will not cut unless pressure is applied to the bar. This will cause excessive wear on the bar and rails. So, modern chains run more side plate angle or hook, if that's the term you'd like to use for it. The reason they do this is it allows it to self-feed better. Changing that angle, a 60-degree angle will self-feed better than a 70 or an 80 or a 90. Back in the era this manual was made, they weren't concerned so much with its ability to self-feed. The reason why, the saws were heavy. If you've got a 20-pound saw or a 10-kilo saw, it will self-feed due to the sheer amount of weight. As saws become lighter, become more important to try and get them to self-feed. As improvements were made in chain design and they could eliminate the vibration that come from increasing that angle, they were able to start offering it. Back slope. That's a file that's held too high. I'll show you guys the description. I won't read it. It doesn't cut. Nothing to grab hold of the wood. You can have that vertical, it'll still cut. That will not. Gullet filing, the internet's favorite subject. A filled-in gullet is caused by not removing the metal in the gullet with a small round file. A filled-in gullet reduces chip clearance and slows cutting. If you leave a lot of it in there for a long time, it can get in the way. Again, we need space for those chips that are formed down there to get the hell out of there. If you're around filing, do you need to excessively dig down? Sometimes. You need to be able to just maintain the height of the file at the correct level. It is difficult. It takes time. Until you know what you're looking for, use a guide. Depth gauge filing problem. Too high. Too high depth gauge will prevent the top plate from cutting wood. Obviously, if this is higher than that, it won't contact anything. Heavy pressure will be required to make the chain cut. This will result in excessive wear on the bar and the toe of the cutters. Too low. See this one a lot. People get excited. Hook right in. Too low depth gauge setting will permit the top plate to grab too much of the wood and make the cutter chatter or bounce. Feels like crap. You get that real bouncy. You know when you got it wrong. The total result will be loose rivets, wear on the heels of the cutters, and broken chain. Again, what it does, the cutter can rock back too far, it slams down the heel of the cutter into the bar rail, and it wears through here. It'll eventually crack to that rivet and it breaks out. Depth gauge filing problem number 3. Too blunt. Modern chains have changed the design of the depth gauge. It would be much more rounded and come down here. This is to try and prevent things hitting up against the front. It is a kickback reducing feature that just about every modern chain from every major manufacturer has. Same issue occurs with them if you just file them flat, or you end up with that front edge. I've spoken about this before in previous videos. Their description here is a flat top depth gauge will hammer into the wood and make the top plate grab too much of the wood as it enters the cut. The chain will run very rough and develop loose rivets. That concludes our manual. If you've managed to make it through this boring video, then I hope you come away with it with some knowledge. I've been searching around for a bunch of old chain and sharpening information, found some great stuff. This combines a lot of very good information into one book, and I thought I'd share it. I have a bunch of other ones. A lot of them have different descriptions for different things, allowing more information. We may go into them over time. We'll see how we go. But yeah, if you made it through this, hopefully you learned something. Hopefully you got a better idea of what's what. And we'll leave it at that.